Okay, hi everyone. Good morning, and this is Moitra here today. And so, welcome to the second day of Precision 2020. So, today the undergraduate symposium is starting with this session. And well, as you can guess from the title, that the symposium's main focus is on undergraduate research, and the talks that are coming actually they are just undergraduate researchers done by the speakers actually. So this is the first astrophysics and cosmology session of the symposium. We will have another one of that tomorrow, and we'll also have sessions of symposium on theoretical physics, condensed matter physics, and material science, and also some interdisciplinary topics. So, just before we begin, just some general instructions that please keep yourselves muted and please keep your videos off because it saves some bandwidth. Also, one another thing is that generally in this symposium, the talks are roughly 12 minutes long, after which we will have a 3 minutes long question answer session for that talk. So we will accept questions, take questions during that question answer session. So you can type your questions as usual in the chat box, or you can also raise your hands. So that's it, and this session will be chaired by Shaugato Barat. So over to Shaugato da.
Thank you, Moitreyo. Welcome everyone to the Astrophysics and Cosmology session of the Undergraduate Symposium. Today we have 5 speakers, and as Moitreyo has already mentioned, the talks are going to be 15 minutes duration, and we are going to have 3 minutes for question answer session and 12 minutes for the talk. Uh, to the participants, I'll let you know after 10 minutes that you have 2 minutes left. Uh, I hope that we can maintain time during this session. And as Moitreyo has already mentioned, that we are going to take question answers after the talk is over. Okay. So I would like to invite our first speaker, Mr. Shuman Pramanik, who is going to talk about detection and theoretical aspects of very high energy gamma ray bursts. Shuman is an alumnus of the Presidency Physics Department, and currently he is a student at IIT Kharagpur. So I would like to request Shuman to please share his screen and go ahead with his talk.
Thank you, Shogato, for the great introduction. So it's showing that host is disabled participant screen sharing.
Okay. Okay, can you share your screen now?
Yeah, I can.
Okay.
Is it visible?
Yeah, it's
Yes.
visible.
Okay. Hello, everyone. I'm Shuman Pramanik. I have done my master's in physics from IIT Kharagpur this year. Today, I'll be discussing about detection and theoretical aspects of very high energy gamma ray burst. I have done this work under Dr. Debanjan Bush at IIT Kharagpur and Professor Resmi Lakshmi from IST Trivandrum. I would like to acknowledge them. Today, I'll be discussing about discovery of gamma ray burst overviews, detectors and telescope. Then I'll be talking about a special gamma ray burst, and then I'll be talking about some models. The talk will be less mathematical. Let's see. Well, so after the nuclear test ban treaty, both Soviet and United States neither trusted each other. So fear from Soviet might try nuclear test, perhaps far side of the moon, from where it can't be detected. Soviet launched a set of satellite system called Vela. Vela were equipped to detect gamma flash from nuclear burst. On 2nd July 1967, Vela 3 and Vela 4 detected a strange kind of flash, unlike anything. The flash contained a gamma peak followed by after emission. And they detected 16 such more bursts and finally conclude that they are not coming from any known source or man-made source, but they are coming from unknown sources. Gamma ray bursts are the high energy gamma emission from cosmological sources for very small time. It lasts for few seconds, and we can compare its total energy with the energy of a star over its lifetime, around 10 to the power 44 joule. So we can think how energetic it is. For just few seconds, we have the energy comparable to the energy of a star over its full lifetime. On a 9 years mission of NASA's Compton Gamma Ray Observatory, the mission is called Burst and Transient Source Experiment. They detected 2,700 GRB positions all over the sky and plotted them in galactic coordinate. In galactic coordinate, we can see that there is no signature of having Milky Way galaxy or other galaxies anywhere. So we can say that whatever the source may be, they are not of galactic origin, rather they are of cosmological origins. We can, from this short video, we can see that any two GRB positions or happening time are not related. They are just happening randomly for time and space. Depending on their lasting time, GRBs are mainly divided into two classes. Short GRBs, they are last for less than 2 seconds, and long GRBs, they are last for more than 2 seconds. The population of GRB versus its duration plot shows two distinct population for short and long bursts. That drives us to think about more fundamental classification scheme rather than their lasting time only. That is basically their origin. They are originated from two different kind of sources. Short GRBs mostly originated from mergers like neutron star, or neutron star white dwarf, neutron star black hole maybe. This kind of mergers, when they merge, there is a certain energy release, and merger takes less time to merge. That's why this kind of gamma ray burst are short gamma ray burst. The second kind is when a star collapse in supernova explosion or kilonova explosion. The core collapse takes some time. That's why this kind of gamma ray burst are the long gamma ray burst. There is another kind, astronomer thinks that when star falls on a black hole, there is a certain increase of the black hole energy system, and that increase in energy triggers some energy emission in terms of gamma ray burst. Whatever the source may be, the end product in most of the cases is a black hole. So whenever we see a gamma ray burst over the sky, we can say that a black hole being born. Gamma ray bursts are the birth cries of a black hole. We know that mergers also emit gravitational wave, and they sometimes also emit GRBs. So collaborative study of gravitational wave and GRB are the best way to understand the applicability of Einstein's gravity and Maxwell's electrodynamic theory in extreme environments. There is lots of physics involvement, starting from electromagnetism to quantum gravity, and lots of astrophysics involvement to understand gamma ray burst. Now, can we see a gamma ray burst sitting on Earth? Actually, we can't, because our atmosphere is opaque for high energy emissions. We only can see visible lights and radio wave. But what we have to do to see gamma ray burst, we have to build satellite telescopes outside our atmosphere, or we can see it with indirect detection, with Cherenkov detection. So there is two kinds of telescopes. These are the known satellite telescope, Cargo, Fermi, Integral. They are basically dedicated to high energy gamma emissions and X-ray emissions. And these are the atmospheric Cherenkov telescope. They detect gamma ray burst with indirect Cherenkov emission method. They are called IACTs, I mean International Atmospheric Cherenkov Telescopes. Well, so typical GRB light curve contain a prompt stage, which is the main burst of the gamma ray burst, lasts for very few seconds, followed by a radio wave. In most of the cases, we only see us after emission. We, in most of the cases, miss the prompt part because rotating the telescope needs some time, and prompt emission are really very small lasting. So in most of the cases, we miss that, but we can see the afterglow. For a long time, Fermi Gamma Ray Space Telescope detect most of the high energy gamma ray burst, but they never detect any of such gamma ray burst of energy more than giga-electron volt. But on 14th January 2019, MAGIC, a ground-based Cherenkov telescope, detected a gamma ray burst of sub-tera electron volt energy that is called GRB 190114C. This was a groundbreaking discovery because now we need to understand the GRB engine to accelerate charge to such a high energy that we can get a gamma ray burst in tera electron volt range. Now we need to understand this physics. These are the plots by MAGIC collaboration. They detected the gamma ray burst also at the same time. X-ray telescope and LAT, they detected the same object, same source with different energy windows. They plotted, and after the extragalactic background light correction, the data points follows well power law distribution. They showed that the data point follows well power law distribution when we plot flux versus time, that is a straight line in logarithmic scale, that called the power law. Now we need to understand some theoretical models for such a high energy gamma emission from a GRB engine. I'll be talking about a model very briefly. That model is something called dynamical model of expanding shell. Let's say GRB happens at the center of this expanding shell, and then shell is expanding. This is basically the scenario. When gamma ray burst happen, that explosion ejects some material, that material called ejected shell material, and then we have a shock wave propagating through the interstellar medium. So the system, we can divide the system in three mediums. The unshocked interstellar medium, that medium doesn't even know that GRB happened because shock wave doesn't propagate through the medium. There is a shock medium, shocked interstellar medium, and there the ejected shell material. So let's develop some equation. What we can do is that we need to understand how the shell is evolving with time. So if we just equate the energy, if we apply energy conservation for time t and some increment of time delta t, t plus delta t, then from energy conservation, we get this differential equation where gamma is the Lorentz factor, is correspond to the velocity of the expanding shell. Basically, I will say that later. So we get this equation. We have also other two equations along with this equation, that the mass of the shell, expanding shell, will increase with the radius as a sphere, and we consider constant density interstellar medium, so it will just follow a spherical law, and the radius of the expanding shell will increase with time with this formula. This is relativistic effect. Basically, gamma is the relativistic gamma, correspond to the velocity. M is the ejected shell mass, and small m is the mass of the shocked medium, the medium 2. Yeah. And T is the observer time. Yeah, gamma is the adiabatic index. Epsilon is the.
You have 2 minutes left.
Okay. Epsilon is the fraction of energy that radiated. So this expansion can be adiabatic or radiative. So we have to take a parameter that is epsilon basically. Well, if we solve these three equations, we get evolution of gamma and evolution of radius after normalizing those equations, because we don't want units in our calculations. There is some free parameters. As I said, the mass fraction is a free parameter of the problem. The epsilon is a free parameter, theta also, viewing angle, and time also. Let's see. If we plot the evolution of gamma and the radius, evolution of radius, then we see that the velocity is decreasing with time. Gamma is corresponding to velocity. That because as the shell is expanding, it collects more and more mass from the interstellar medium that cause the deceleration of the cell. We can see the deceleration from the radius plot also. Firstly, it increased linearly, then there is a deceleration stage. And in the logarithmic scale, the radius versus gamma plot follows a straight line. Well, if we plot for different epsilon, if it is radiative process or if it is adiabatic process, that cause a difference in the plot also. If we plot for different viewing angle, that also cause difference, but gamma versus radius plot will not change because it is the intrinsic property of the blast. It doesn't depend how we see the gamma ray burst, and there is a dependency with initial time also. Well, these are the reference of my talk. Uh, thank you. I'll be happy to have your questions if you have any question. Thank you.
Thank you, Shuman, for the wonderful talk. Now I would request everyone if they have any questions. Then okay.
Can you hear me?
Yeah.
Yeah, you got cut, Shogato. So did you ask me to ask the question?
I asked.
Okay. Shuman, can you hear me?
Yes, sir.
Yeah, so I was just wondering that, there are many free parameters in the model. So among them, the gamma that you took as 100, is there a particular reason to choose that number 100?
Sure. So we have to start with some initial parameters to solve these differential equations, right?
Yes.
Now I choose gamma as 100. No, there is no reason. I can choose it 200 or 300 also.
Can
But
you choose less? Can you choose 5 or 10?
yeah, then that will be a different case. So 5 or 10, this is for X-ray burst case. We are doing with gamma ray burst. This is some high energy engine. So I
Why
think
is that? I mean, why is it a problem to take lower gamma?
It is not a problem. We still get a solution, but the solution may not as our required system. We want solution of high energy uh, systems, right? So tera electron volt emission for, let's say. But the small gamma, if we start from small gamma, that means small velocity, initial velocity. So what we are assuming that the initial thrust is very high, that basically the gamma naught, the initial thrust of the expanding shell. And for high energy emission, that should be high value. Or low gamma naught.
Okay, I understand your point. I mean, even for lower gamma, you can produce high energy gamma rays. I mean, Blazars have gamma of 5 or 10 and they produce very high energy gamma rays. So that's not exactly the, but it's okay. I mean, I understand your point.
Okay. So if anyone has any other questions, they can please go ahead and okay. Okay. So Obhinanda Chakraborty has a question. You talked about different sources of GRB. So my question is, from GRBs, can we infer how it has been originated?
Sorry, can you please repeat?
Yeah, sure. Uh, you have talked about different sources of GRBs. So my question is, from GRBs, can we infer how it has been originated?
How it has been originated. So yeah, these are the sources like mergers or uh, supernova explosion. This is the origins.
I think can I just interfere for a second?
Yeah.
So I think the question is that just by looking at GRB emission or whatever other properties, can you tell that from which source the GRB happened? I think that is the question.
So for that we have to do some spectroscopic analysis. I mean, in case of supernova explosion, there is some signatures, and for mergers, there is some signatures in the spectroscopy. If we do that, we cannot certainly tell, but we can think that this may be the source. And also for mergers, there is at the same source there is gravitational waves also for the same source. That we can say that this is the source. It's merger or supernova from the spectroscopic signatures.
Okay, thank you. Okay. Ognivo Datta has written that there is a YouTube question. Is GRB in any way related to cosmic rays?
GRB's cosmic rays are basically the charged particle coming from cosmological sources. So GRBs, when there is emission, that there is also plasma, uh, charged plasma emission from the GRB. So along with the gamma emission, there is also charged particle emit. So that may cause some cosmic ray as cosmic ray source, but the problem is that we can't point the cosmic ray source because there is certain magnetic fields and electric fields all over the its travel path. So it may bend. So we can't pinpoint from which source it is coming. But yeah, GRBs are may cause of cosmic rays. Yeah.
Okay, thank you, Shovan. So I think we are running out of time. So I think we will move on to the next talk now.
Thank you.
The next talk is by Otishwan Khashnovish, and he's going to talk about X-ray variability of a Blazar MRK421 from AstroSat data. And currently, he's a student of Presidency University. So I would request Otishwan to please share his screen and go ahead with his talk.
Yes. Can you see my screen?
Yes, we can see.
One second. Yes. So, hello everybody. Am I audible?
Yeah.
Yes, you are audible.
Okay. So my name is Otishwan Khashnovish, and I did my BSc from Presidency University, Kolkata, and I am going to talk about the project that I did during the 6th semester of my BSc under the supervision of Dr. Ritoban Chatterjee. And as you can see from the title of my talk, that I'm going to talk about the X-ray variability of an astronomical object called a Blazar, named as MRK421 in my case, using AstroSat data. So first, I'm going to talk about a little about the active galactic nuclei. So these are basically compact regions at galactic centers. Uh, their luminosity is comparable to that of an entire galaxy. So it's about 10 to the power 46 cells per second. And for normal galaxies like the Milky Way, for example, it's roughly around 10 to the power 44 ergs per second. So it's about 100 times brighter than ordinary galaxies, 100 or 1,000 times. So we get emission from these objects in multiple wavebands. We can sometimes see very strong radio emission from them, right up to gamma rays, in fact, TV gamma rays. So one a very important feature about these of these things is that their spectra have emission lines in these active galactic nuclei spectra, and that is quite distinct from stellar spectra or galactic spectra because they are generally characterized by absorption lines, and 10% of these AGNs have jets, and those AGNs are very bright in their radio wavelength. So we can classify AGNs based on the presence or absence of jets. So the AGNs which have jets are called radio loud AGNs because they are bright in radio wavelengths. And the other one is the radio quiet AGN. So the radio loud AGNs are further classified based on their orientation with respect to our line of sight. So if you can see this figure, we are seeing this structure from the edge-on point of view. So if this is the case, then there is a supermassive black hole at the center, which is surrounded by an accretion disk, and that is obscured by a dust torus. So if we look at it edge-on, the accretion disk is not really visible. So the most of the luminosity of this structure is coming from the jets, which is very bright in radio. So these objects are called radio galaxies if it is viewed edge-on. If the jets are pointing towards us, then it's called a blazar. We are looking at that structure then face on, and if it in some intermediate angle, then it's called a quasar. So the blazar, I'm going to talk about the blazars in this talk. So blazars have the following characteristics. Because the jets are pointing towards us, the jets are jets of relativistic charged particles, and these, because of they are pointing towards us, so the radiation from the jet is Doppler boosted because of relativistic beaming, and because of that effect, the jet radiation is dominant over other parts of the AGN. Like, for example, the accretion disk of the AGN is intrinsically much brighter than the jet. But in case of blazars, because the jets are pointing towards us, the radiation from the jet dominates over the other parts of the AGN, from the other parts of the AGN. So I'm going to talk a little about the AstroSat. So this is India's first dedicated multi-wavelength space telescope. And the importance of this thing is that we can make simultaneous observations at different wave bands, from UV right up to hard X-rays. And for my work, I have used the soft X-ray telescope of this satellite. It's also called the S16 short. And the soft X-ray telescope uses X-ray reflecting mirrors and X-ray CCD for timing and variability studies from 0.3 to 8 keV band. So this band is basically the band for soft X-rays. And the X-ray CCD is basically a silicon CCD which creates photoelectrons when X-ray photons fall on it. And this diagram actually shows how an X-ray telescope, like the soft X-ray telescope, works. So basically, X-rays are falling on these set of mirrors at grazing angle of incidence. So because of that, they are reflected to a point that is the focus, and where the X-ray CCD is placed, which forms the image. And this is basically the structure of in the internal structure of a X-ray telescope like the S60. So then this is basically the data analysis techniques that I have used for this work. So there are different levels of data, say the first level of data is the raw binary data, which obviously we cannot use, and we can actually apply transformations to the level 0 data to obtain level 1 data and level 2 data. So the level 2 data is the final data that we use, and for converting level 1 to level 2 data, we use a software called S60 pipeline. And because we obtain data files from different orbits of the telescope during its observation of this source, in my case, it's Markarian 421, MRK 421, we have to merge all the data files together into a single file. For that, we use a software called S60 EVT merger tool or S60 event merger tool. And then for extraction of image, light curve, and spectrum, we use a software called XSelect. And there is background noise, which we need to eliminate while obtaining the image of the source. So we use a software called L-curve. And the energy range for observation. Hello? Hello?
Please go ahead.
Oh, okay.
Just one.
Yes. So the energy range for observation is 0.3 to 8 keV, which is basically the soft X-ray band of the electromagnetic spectrum. So this is basically the light curve, the X-ray light curve that for MRK 421, which has been obtained during 23rd, 28 April of 2019. And I've basically shown this same light curve again with a difference in the binning time. So the binning time is basically you divide the time axis into several bins of, say, 600 seconds in this case. And you basically take average of all the data points in those bins. And so if you take the average over a large number of points, so the error bars get reduced, and also the total number of points also get reduced. So for 1800 seconds, you have less number of data points. So this is basically the extra light curve, which I have extracted from the AstroSat data for the Markarian 421 Blazar. So I'm going to talk about the possible causes of variability that we obtain, that we observe from this Blazar. So the Blazar emission is mostly from the jet, as I had already said, because the jet radiation dominates over other parts of the AGN. And the emission mechanism is primarily synchrotron radiation. In my case, we can say this because if we look at the spectral energy distribution of the Blazar, then we can see that there are two peaks. There are two humps basically, and the first hump is called the synchrotron hump, and the second one is an inverse Compton hump. The synchrotron hump basically peaks at this particular energy range, in the soft X-ray energy range. So the soft X-ray emission at least comes because of synchrotron radiation from the jet. And this synchrotron radiation basically means that there are electrons and they are spiraling around magnetic fields, B fields. So there are magnetic fields in the jet, and the charged particles which are moving at relativistic speeds, they are orbiting around those magnetic field lines. And because a charged particle, when it's accelerated, it radiates electromagnetic radiation. So we get EM radiation from that. For synchrotron radiation, this is the expression for the rate of energy loss from the electrons. So dEdt is basically, it's like a rate of cooling. So this is the expression. So sigma t is called the Thomas scattering cross section. C is the speed of light, and U mag, you can see here, it's B squared by 8 pi, it's in CGS, and this is the energy density of the magnetic field. Gamma is the Lorentz factor. So from special relativity, we know that gamma is basically 1 over root over 1 minus v squared by c squared. And this alpha is basically the angle between the velocity vector of the charged particle and the magnetic field line. So one of the properties of synchrotron radiation is that it's polarized. Like if the magnetic field line is pointing towards us, it's aligned with respect to our line of sight, then we get circularly polarized light. If it's in the perpendicular direction with respect to our line of sight, then we get linearly polarized light. And if it's in somewhere in between, then we get elliptically polarized light. So the frequency of radiation emitted as a result of synchrotron radiation is given by this expression where this 10 to the power 6 is just a constant. Gamma square is the Lorentz factor squared and magnetic field. So if I set B equals 1, then for optical photons, we know roughly the frequency is about 10 to the power 14 hertz. And then from this formula above, we get for optical photons, gamma equals 10 to the power 4. And similarly for X-ray photons, I mean soft X-ray photons, that's roughly 10 to the power 16 hertz photons. The gamma is about 10 to the power 5. So the energy loss rate, as we can see from the previous expression, it's proportional to gamma squared. So the optical flux, we can say, roughly falls 100 times slower than the X-ray flux. So this is from the theory. So it's like 10 to the power 5 divided by 10 to the power 4 whole square. So that's 100. So the optical flux should fall. The optical flux variability should be 100 times slower than the X-ray flux variability. So this is basically the simultaneous optical light curve that has been obtained using two telescopes, Korean Astrophysical Observatory and St. Petersburg State University telescope. So this is simultaneous data. So it has been taken during the same time when the X-ray data was being taken by Astrosat. And the next one is the infrared light curve of the same source, Markarian 421. So here you are basically seeing two light curves because they are two different bands of the infrared spectrum, infrared part of the spectrum. One is called the J band and the other is the H band. So this is basically near infrared. It's about some 1200 nanometers to 1600 nanometers. And
Otishwan,
yes.
You have 2 minutes left.
Okay, fine. So in this particular graph, I have shown that the green points that you see in the background, that's the X-ray variability. So it's real data. And I have basically superposed the optical light curve on this data, on the X-ray data. And in the next graph, I have basically tried to predict how the optical flux varies from the X-ray flux. So we know the X-ray flux from the Astrosat data. Now, this green line that you see, this is not real data. This is basically predicted from the X-ray flux. So it's like the X-ray flux is not changed, but because the optical flux should vary 100 times slower than the X-ray flux, as we have seen from the theory of synchrotron radiation. And so what we are doing is that we are multiplying each of I mean, we are expanding the time axis of the X-ray variability by about 100 times. And so it's like we are trying to say that the optical flux is nothing but it's similar to X-ray flux variability, but as if it's not over 5 days, but it's over like 500 days. But we are not observing for 500 days the observation of the optical flux. We are observing just for the 5 days, and that shows the variability of the optical flux. And I can say that this is comparable to the real data that I have seen. So it's like predicting the low frequency energy variability from the high frequency ones, like the X-ray variability. It would be the same for infrared as well, but infrared flux would vary much slower even because the frequency is lower and the gamma is lower than the optical one. So this is basically my summary. So I've basically analyzed the X-ray data of Blazar from a 60 instrument onboard Astrosat to produce the 0.328 keV light curve. And also that the X-ray emission is mostly from the synchrotron radiation. I have also studied that. And assuming that lower energy emission from MRK 421 is also due to synchrotron radiation, like the optical emission, I've tried to theoretically predict how the optical flux varies from the variability of the X-ray flux, and I've compared my prediction with optical and near infrared telescopes. So the higher frequency radiations like hard X-rays are mainly due to the inverse Compton scattering, because that's also we can also see that from the spectral energy distribution. And that's my future work. I plan to work on it in the future. So these are my acknowledgements, and thank you.
Thank you, Otishwan, for the wonderful talk. I think we already saw a couple of questions in the chat box. So first, we have a question from Otishwan. Oritrakundu,
Yes.
what kind of transformations are you using to get level 1 data from level 0 data?
Okay, so level 1 data is basically available in the we do not really get the level 0 data from if we even try to analyze it in that case, because if you use the SXT pipeline and the source of the data, we first get the level 1 data and you use SXT pipeline to reduce that to level 2 data. So level 0 data is basically the binary data, so that's not publicly available, I think.
I see that Shomodip sir has raised his hand. Sir, could you please go ahead with your question?
Well, my question is that can you hear me, correct?
Yes, yes, yes.
Okay. So you are trying to match the optical prediction with the observation.
Yes.
Have you made any quantitative study of that, or just looking at by eye you are saying they are similar?
No, I haven't really made quantitative study of that. That's true. But if we think about the relative fluctuation, I think it's comparable. Yes, but yes, I have not really done much quantitative study about that. Yes.
I guess that will be much better to make any quantitative.
Yes, yes. I think I would like to do that in the future to make a comparative quantitative study.
Thanks.
The next question is from Onik Parvi. In the infrared light curves, you mentioned H and J band. So my question is, what are these bands signifying?
No, they are just basically two different bands corresponding to two different wavelengths. Like the J band is the midpoint of the J band is about 1220 nanometers, and the midpoint of the H band is about 1630 nanometers. So that's just two near infrared bands. So the width of the J band is about 200 nanometers, and the width of the H band is about 300 nanometers. So uh, that's just the wavelength. So there are two different parts of the infrared band of the electromagnetic spectrum. So it's nothing different. But obviously, the frequency of the infrared band is much lower as compared to the optical. So, so I basically just wanted to wanted to show that how the low frequency varies if we try to predict it from the high frequency variability, like the X-rays.
Okay. So we have our last question that is from Onkita De. We always get polarized light from synchronized emission. If you could explain a bit.
Okay, so synchronized, I think, is not the correct word. Synchrotron radiation, I think. So
Synchrotron. Yes.
yes. Well, yes, that's true. For example, the magnetic field line, the electron is basically gyrating about the magnetic field line. So that means that the electron is moving in a helical path about the magnetic field line. And if the magnetic field line is like perpendicular to our line of sight, so we basically see the acceleration vector of the electron, which is basically in the radial direction, right? So it's the centripetal acceleration. So that the acceleration vector is basically going up and down if the magnetic field is perpendicular to our line of sight. So we get linearly polarized light from that in that case. So that is one situation. And if the magnetic field line is pointing towards us, it's oriented with respect to our line of sight, then we can see circularly polarized light because the plane of polarization of the emission from the electron, it's basically rotating. So for that we get circularly polarized light. And if it's in somewhere in between, the angle is not really 90 degree or 0 degree with respect to our line of sight, then we get a superposition of both the circular and the linearly polarized light. So that's elliptically polarized. So that's how we get polarized light from synchrotron radiation. And but in this case, we cannot really do polarimetry because polarimetry for X-rays is not really very we cannot do that. It's not very easy to do polarimetry for X-rays. So, but for lower frequencies like optical and infrared, we can do polarimetry, and we can guess whether it's from synchrotron or not. That's it.
I hope that
You're getting cut. We cannot hear you. Hello?
thank you,
Yep.
Otishman. So thank you for the wonderful talk, and I think we are going to move on to the next
So I'm stop sharing.
Talk in the session. So yeah, the next talk is by Shashank Dattatri, and he's from IISc Bangalore. He's going to talk about stellar capture rates in galactic nuclei containing supermassive black holes. I would request Shashank to please share his screen and go ahead with the talk.
Yes, hello. Can you hear me?
Yes,
Yes, you're
I
audible.
can hear you.
Yes, good morning, everyone. I'm Shashank from the Indian Institute of Science, and I'll be talking about stellar capture rates in galactic nuclei containing a supermassive binary black hole. And I did this work alongside Professor Arun Mangalam of the Indian Institute of Astrophysics. Let's get right into it. So simply put, the nucleus of a galaxy refers to its central region. Of course, the size of the nucleus depends on the various properties of the galaxy, like its mass and its morphology. But typically, the size is of the order of a parsec to a few parsecs. And various unique dynamical processes take place inside the nucleus. So the stars and the gas inside the nucleus behave very differently compared to the outer regions of the galaxy. And nowadays, we believe that almost every large galaxy contains a supermassive black hole at the center. For example, our own Milky Way galaxy has a supermassive black hole named Sagittarius A star, and it is about 4 million times the mass of the sun. And the study of supermassive black hole and the effects on the surrounding stars and star clusters has become a very active and evolving topic of research over the past few decades. So I'll be looking at one specific aspect of supermassive black holes, that is the capture of stars that wander too close to it. And this capture can result in the tidal disruption of the star. That is, the star gets ripped apart by the extremely strong gravity of the black hole. And such a tidal disruption event can be observed from Earth as a luminosity flare for a few months. So here is an artistic impression of a star getting tidally disrupted by a black hole. I'm sure all of us have seen something like this on the Discovery Channel. However, black holes do not remain in isolation forever. According to the standard lambda cold dark matter paradigm of structure formation, it states that bigger galaxies are formed from the merger of smaller galaxies. So during a galaxy merger, initially the field stars of the galaxy interact through violent relaxation processes. And this field of galaxy merger is itself a separate and very fascinating field of study. But eventually we are left with a binary black hole system. And I'm going to be talking about, I'm going to be focusing on binaries with unequal masses. And we're going to examine how the capture rate and tidal disruption rates are affected in the presence of a binary black hole. So here is an artistic picture of a binary black hole in a galaxy. So our setup consists of a primary black hole of mass m1, a secondary black hole of mass m2 equals q times m1. Here, q is the mass ratio, and we take q lesser than 1. That is, m1 is much more massive than m2. And also, we assume that m1 is fixed at the center of the galaxy, whereas m2 is spiraling towards the center, towards m1. And there is a stellar cusp that is centered around m1. The density of the cusp follows a simple power law, rho equals rho naught times r by r naught to the power minus gamma. The motion of the stars of the cusp is affected, obviously it's affected by the presence of the primary and secondary black holes, but also the stellar cusp itself has a gravitational potential. So the cusp sort of affects its own motion. And since we are dealing with supermassive black holes, general relativity also plays a very important factor. So in the standard Kepler problem, that is the two-body problem, we know that the motion takes place on a plane in the form of a static ellipse. So the eccentricity, the inclination are both constant, and therefore the angular momentum is constant. However, if the motion is perturbed by a distant perturber, the dynamics works out differently, and the eccentricity and the inclination can be exchanged. That is, the eccentricity can decrease while the inclination increases, and vice versa. So this allows the angular momentum to oscillate, and this is known as the Lidov-Kosai mechanism. However, the Lidov-Kosai mechanism is not the only thing at play here. It can face competition from the stellar potential and the GR effects. So here's a diagram illustrating the Lidov-Kosai mechanism. Here, the central body is the primary black hole. The perturbing body is the secondary black hole. And we are looking at the motion of a field star as the test particle. So initially, the orbit can have low eccentricity and high inclination. But over time, it can exchange its inclination for its eccentricity. So it can become a high eccentricity, low inclination orbit. And high eccentricity means that the angular momentum decreases. So the three dominant mechanisms at play here are the stellar potential, the Lidov-Kozai mechanism, and general relativity. All of these induce precession of the pericenter of an orbit. So the total precession rate is due to the sum of all three contributions. And now it just becomes a game of which mechanism dominates. So it turns out that when the binary separation is very large, the stellar potential dominates, whereas at very small separations, the general relativity dominates. And one key point to note is that the precession due to stellar potential is opposite to the precession due to GR, so they can cancel each other out. And meanwhile, while all of these stellar dynamics is happening, the binary system is itself continuously evolving. So at first, the inspiral is due to dynamical friction, but later on, dynamical friction becomes ineffective, and the evolution is mainly due to three-body processes. And since the effectiveness of each of the stellar dynamic mechanism depends on the binary separation, so this means that there's a brief period of time during the binary evolution when the competing mechanisms sort of cancel each other out, and the Lidov-Kozai mechanism is able to dominate. So we recall that the Kozai mechanism leads to angular momentum oscillations, and now we're going to see why this is very important. So now let's discuss some of the dynamics of capture. The tidal radius of a star of mass m star and radius r star is defined as r tidal equals r star times m by m star to the power 1 by 3. Here, capital M is the mass of the black hole. And if a star enters a region within r tidal, then it gets captured by the black hole and it can get tidally disrupted. So let's consider an orbit which has a pericenter distance just equal to r tidal. And this orbit will have an angular momentum equal to root 2 gm r tidal. And obviously, if an orbit has angular momentum lesser than this LLC, then this can get captured by the black hole. And all such orbits is called a lost cone in total. So the tidal disruption rate is determined by the flux of stars into the lost cone. And many studies have shown that the average rate is about 10 power minus 5 to 10 power minus 4 events per year. So this is one event per 10 power 5 years per galaxy. And this is the average rate for a single black hole system. But now let's look about what happens if there's a binary. So we saw that the Lidov-Kozai mechanism induces angular momentum oscillations. So let's consider a star which has an initial large angular momentum greater than LLC. So under normal circumstances, it wouldn't be able to get disrupted. But because of these oscillations, the angular momentum can now oscillate to below LLC, so it can become a candidate for capture. So effectively, this increases the size of the lost cone, and it increases the flux of stars into the lost cone, and the capture rate drastically increases because of this. So let's look at the results here. I've plotted the binary separation in red and the capture rate in black. So initially, the Kozai mechanism is not effective, so the capture rate is low, of the order 10 power minus 5 events per year. However, there's a brief period of time when the capture rate shoots up considerably to over 10 power minus 2 events per year. So this is a huge increase of almost 3 orders of magnitude. And eventually it comes back down as the separation reaches the binary separation reaches the milliparsec scale. So the general results are as follows. The peak capture rate is about 2 to 3 orders of magnitude greater than the ambient capture rate of a single black hole system. This capture rate reaches an enhanced phase and then it comes back down. The enhanced phase starts when the binary separation reaches about 1 parsec and it ends at about 0.1 parsec. And the duration of the enhanced phase is about 10 power 5 to 10 power 6 years. So in conclusion, we have developed a model for the capture rates in binary black hole systems. And since the rate is much higher than single black hole systems, the tidal disruption event rate can be a powerful method to identify supermassive black hole binaries. We calculate how many tidal disruption events will be observed on Earth by performing a cosmic integral over the cosmic volume. So this will give us the total number of events and the number of events that will originate in binary systems. So specifically because the rates of binary systems are so high, there is a possibility of observing multiple events from the same galaxy during the survey. So let me explain this. So since the single black hole rate is so low, it's about 10 power minus 5 per year. So say during a typical 10-year survey, the probability of even observing one event is very low, so let alone multiple events. However, during the enhanced phase of a binary black hole, the possibility of observing multiple events becomes quite real. So such an observation would be indirect evidence of the presence of a binary black hole. And at present, the detection of binary black holes is quite a challenge. One popular method is through gravitational waves, but these are only applicable if the separation is very small, like in the milliparsec range.
Shashank, you have
Yes?
2 minutes left.
Okay. So our method, the analysis of the tidal disruption event rate, can be a powerful method to detect binaries within where the separation is from within a parsec to a few subparsecs. So our new model will provide, we are confident that our new model will provide more accurate predictions for the observable event rate, and this will lead to new exploration in the field of galaxy mergers. Thank you.
Thank you, Shashank, for the wonderful talk. Now it's time for some questions. We have a question from Protushava Boral. What are the typical values of Q? And also, till what redshifts are these SMBHP events observed?
Yeah, so the value of Q is actually a very wide range. It can go from, it depends on what we are examining. If we are examining major mergers, that is two equal mass galaxies are merging, then the value of Q is 1. But whereas if it's a minor merger, then it can become as low as 0.01, 0.001. So it's a very wide range, and it just depends on what you're looking at. I've been focused on minor mergers, so I've taken low values of Q in my work. And up to it, the redshift up to which these events are detected also depends on the the mechanism of capture. So this itself is a completely separate field. Once a star is tightly disrupted, it's going to form an accretion disk around the black hole, and the fallback of the accretion disk into the black hole is what causes the luminosity flare. So typical values of this redshift for solar mass stars would be around 0.5 to 0.7. That's around the range for solar mass. But again, it really depends.
Hello?
Yes. Yeah, that's it.
Okay, thank you. So I think I can see several hands raised in the box. So I'll first request Ritoban sir to unmute himself and ask his question.
Yes, can you hear me?
Yes.
So I had a couple of questions, but let me ask just one now, and it's related to what Pratyushavu asked. So you have a very specific result of, the rate increases by, or 3 orders of magnitude for a very specific distance, binary separation, and very specific period. I was wondering, shouldn't that depend a lot on the mass ratio? I mean, shouldn't that result be if there should be a parameter, mass ratio shouldn't be a parameter in that plot?
Yes, of course it is a you're talking about this plot, right?
Yes, that's right.
Yeah, so this plot is for the specific case of the primary black hole is 10 power 7 solar masses, and the mass ratio is 0.01. But the general result is that as long as it's a minor merger, so the mass ratio is low enough, we are going to observe several orders of magnitude increase. And I've just plotted this one particular plot for this presentation. But this increase is a very general result, actually, not just for that one specific set of parameters.
Okay.
Thank you, sir. Next, I would like to request Shomodip sir to unmute himself and ask his question.
So my question is, why do you get a peak kind of profile? Why does it decrease afterwards when the binary separation decreases?
Yes. So I explained about the competing mechanisms, right? The stellar potential and the GR mechanisms, the GR effects. So when the binary separation reaches very low, about 0.01 parsecs, that is when GR effects start to dominate, and these angular momentum oscillations will no longer be there. So once GR starts dominating, we are not going to have a peak anymore. And,
so it's very delta function kind of region where you will have the enhancement.
Yeah, so in the cosmic, over a cosmic time, it looks like a delta function, but actually it is of the order of 1 million years. So it is, so the window for observing these enhanced phase of tidal disruption events is quite large for us. So that's why I'm saying future prospects of this work would be to analyze how many, like in the window of observation for us, how many such enhanced phase binaries would we detect, and how many can we observe on Earth?
Okay, thanks.
Sir, I think next I'd like to request Suchetana ma'am to please unmute herself and go ahead with the question.
Okay, thanks, Shogata. Shashank. So I guess my question is related to what the others, is very closely related to what others asked. So you are looking at stellar capture rate because of supermassive black hole merging, right?
Yes.
And you are saying that there's enhancement in the stellar capture rate because of the merger, but of course that depends on what's the mass ratio is, and what's the distance is, and how far we are looking, etc. observationally. So my first question is that are you just discretely merging to supermassive black holes? Because you understand that when there will be a supermassive black hole merger, that would be accompanied by galaxy merging. So there will be all these environmental issues that will play a role there. So have you considered that, number one? And number two, when you talk about this effect, what do you expect observationally? I mean, yes, there might be an enhancement. It's a very picky profile because you are only using certain kinds of parameter. But suppose you want to make a prediction that this has to be observed with so-and-so telescope. How would you do that? Did I make my question clear? Yeah.
Yes, thank you for the question. So about the first question, we haven't considered the dynamic evolution of the field stars itself. We have just assumed that there's a power law cusp centered around the primary. Of course, your point is absolutely valid. There will be the environment around the black holes will itself be disturbed. But
Yes.
for our simplified model to obtain, our goal for this was to obtain some analytic results and scaling relations. So we have assumed a simpler model of a static cusp, which is centered around the primary. So yes, we could. One of the future prospects would be to analyze how the environment itself evolves during a merger. And secondly, yes, one of the future goals is to we have to do an integral over the cosmic volume, and this would include the merger rates as a function of redshift and as a function of distance. So we plan to do an integral over the cosmic volume, including these merger rates and the black hole mass, to determine how many of firstly totally how many tidal disruption events will be observed, and secondly, how many of these would have originated in.
Okay, so then the
binary
question is that when there is this tidal disruption or when this stellar capture, what is the observational signature? You understand, right? You calculated a number,
yes.
but what do you actually see observationally?
Observationally, there's a tidal disruption events actually have a very specific light curve, and so it has a t to the power -5/3 light curve, and this is a very characteristic signature of tidal disruption events. And this the luminosity flare would be going on for a period of like it depends on the mass of the star that is being disrupted, but it goes on to a few months to even a year. So this t to the power -5/3 light curve is the characteristic of a tidal disruption event. This is the
okay, thank you very much. Yeah,
thank you.
Thank you, ma'am, for the question. I can see that there are more questions, but we are really running late on time. So, if there are more questions, I would like to request everyone to message Shashank personally and get in touch with him. I'm sure he would be very happy to answer your questions. Um, Thank you, Shashank, for the wonderful talk. So, now we would move on to the next talk in the session, and that will be delivered by Ketan Sang, and he's going to talk about F FRB 180916, periodically repeating radio source of extragalactic origin, and he's from the University of Delhi. So I'd like to request Ketan to please share his screen and go ahead with the talk.
Hello, you can hear me? Hello?
Hello.
Yeah, you can hear me?
Yes, yes, I can hear you.
Okay, you can see my screen?
Yeah, I can see your screen.
Good afternoon, everyone. My name is Ketan, and I have done my master's from University of Delhi. Presently, I am working with Dr. Vishal Gajja and Professor Bharchan Joshi at NCRA on fast radio bursts or FRBs. So, seeing the title of the talk, I want to make it very clear from the start that this guy is not responsible for it, although it would have been nice if he was there out there. But no, so this is definitely an astrophysical event. So in this talk, I'll first tell you about what FRBs are, and then I'll tell you what's my work on FRBs, and then I'll come on this particular source of what's so special about it and what is happening out there. So many of my friends have talked about transient events. There's a lot of transient events happening out there, and they're extremely powerful, and they tell us a lot about what is happening in the universe. So there are also transient events which are majorly observed in radio wavelengths. The famous example is pulsars as well as rotating radio transients, which we see. So what happens when we see a pulsar signal in a radio data? We see something like this. This are like evenly spaced pulses, and so it looks very beautiful in the data, and like you can figure a lot out of it. So in this particular plot, I want you to concentrate on this thing, DM. DM is kind of the most important thing in the study of radio transients. So what is DM? DM stands for dispersion measure. So like it's very well understood that when a light passes through a prism, it turns from violet to red. But in case of radio wavelengths, we like in place of prism, we have actually an ionized medium. So when radio wavelengths pass through an ionized medium, same thing happens. What happens is the higher frequency comes first and followed by the lower frequency. This creates a very nice sweep in the data. So using this sweep, you can actually calculate the DM to the source. And what happens is that the DM is proportional to the column of electron density between you and the source. So if you can model the electron density between you and the source, you can estimate the distance to it. So it's a pretty cool property so that will tell you a lot about how far the source is and what is in between us and source. All right. So in 2007, Duncan Lorimer and his student David Narkovich were studying pulsars in Parkes radio telescope data in Australia. So what they found was one single pulse. This pulse was extremely powerful, 5 millisecond wide. But what was odd about this pulse, it came from the direction of large magnetic cloud. And what was odd about this pulse was that only this much part of the dispersion measure could have been attributed to the galaxy. So what was happening was something very interesting. This source was definitely extragalactic. And in the coming years, many of the few more of these sources were found, and they led to an outpour in the uh, uh, projection models. And a lot of models came into picture, but at one point the situation was such that there were more models than actual FRBs in the. So mostly they were attributed to compact objects, of course, because they are the only one who are capable of such level of power. But some people also came with bit unusual models, and many of them have been now a bit of like thrown out because of obvious reasons. So, okay, everything was going well and good. We were getting this powerful burst all over the sky. And then came FRB 121102. This one was a game changer. It was found, it was observed by Arecibo Observatory, and it was also the first FRB to be observed by a telescope other than Parkes. But what happened that in 2015, 10 more bursts were detected from this source. So this was a first repeating source of FRBs. So people decided to take a look of what's happening actually. So they were able to localize it, and they were able to localize it to a nearby to a dwarf galaxy around 3 billion light years away, which was very exciting to find that we all now have our host galaxy, and maybe we can put some guess on what type of environment FRBs thrive in. So this FRB is now the most studied source in this field. There are more than 1,000 bursts right now, and it has been observed in a wide range from like 4 megahertz to 8 gigahertz. But what I want you to look into this is this particular structure. This structure was not seen in other single events, single FRB events. This was part of this source, particular repeater source. And the interesting part is that the repeaters which we have more repeaters now, and the repeaters we have now also show this structure. So people are trying to figure out why this particular kind of downward distinct structure is seen in the spectra. And this might help us tell a lot about what is happening out there. So, okay, fast forward to present time. This is the basic summary of what we know about FRBs right now. There are 130 sources. There are 21 repeaters in the data. They have observed it from wide radio wavelength with varying flux density. A few of them have been localized to their host galaxies from a resistive range of 0.03 to 0.66. Many models are there. There are some interesting spectral temporal properties shown by these events. And some also show 100% polarization. So that's also a good sign to model around what is happening. And the current predicted rate is that around 1,000 or even 10,000 are happening all over the sky. We just have to look for them. So yeah, I work at NCRA, and I do work on the FRB survey using the Giant Meter Wave Radio Telescope. So I use the Sunduck pipeline, which is developed by Dr. Vishal, and we find FRBs in the frequency range of 300 to 500 megahertz. So let me tell you in a very generalized way of what Spunduck does. Spunduck takes an input filter bank file. A filter bank file can be thought of in the sense that it's a 2D array of frequency and time data. And then this file is cleaned for RFI using an RFI find algorithm. Then we have an algorithm called Heimdall. Heimdall does a single pulse search, but Heimdall generates a lot of false positive and candidates. So those have to be eliminated, and we use Python. We have designed a Python software for that, a package for that, and we are using it to eliminate false positive candidates. And then we just plotted. Then luckily, since there's like too much of data coming up, and we have like thousands or hundreds of bursts in our data, we are also trying to incorporate machine learning into it so that the steps become faster and more efficient. So as I said that we see the plot. So this is the candidate plot which we see. It has 4 panels. The first one shows you the candidate pulse or the burst in there. Then there is the de-dispersed waterfall plot. What happens is that the sweeping signal is de-dispersed into a straight line using the Heimdall software. So that's what is plotted here. And then there is an on and off pulse plotting so that we can be much more clear of what is happening, whether the signal is astrophysical or not. Then what we have is called the butterfly plot. It's a dispersion measure versus time plot. So if you see a very nice bow structure and the right hand side shows you a good peak, then you can say that this is a good astrophysical candidate at that particular DM. Lastly, we show a panel of like a chunk of the original filter bank data in which the pulse was detected. So it's a pretty interactive plot and helps you understand a lot of what is happening there. So what I basically do is I help in the visual analysis of the candidates generated. So I have analyzed more than 100,000 plots by now. And I also help in cataloging data of like what pulses did we see with our pipeline, what is the efficiency of the pipeline, what is the sensitivity which we can go down to. Then I also help in improving the plots because GMRT is not in a very radio quiet zone. So there are a lot of RFI around. So a lot of cleaning has to be done so that before you can get the data. And then I'm also providing candidates to the machine learning so that it can be trained on GMRT data and incorporated in the pipeline. So now let's come to the main man. FR16 were discovered by Canadian Hydrogen Intensity Mapping Experiment called CHIME. And it is one of the game changers in this field. This telescope is detecting around 30 to 40 FRBs every week. So it's really improved our source count. But this FRB was pretty close, and then CHIME started detecting more and more bursts. So it definitely was a repeater. But then it threw us at a surprise. CHIME analyzed the amount of data which was with them that burst, and they found that it was periodic inactivity. They found that this particular FRB became active after every 16.35 days for a 4-day window, and and it was not very clear of what was happening. But the thing was we actually knew that there is a source which is periodic. So we tried to take a look, and we localized it to a spiral galaxy at the redshift of 0.03, around 150 megaparsec away. It's a massive spiral galaxy in a V-shaped star-forming region. So this was a good hint that the source is coming from a star-forming region. But the part was that this galaxy was not same as the one we have for 121102. So yeah, it raised more questions that what is actually like what is happening actually out there. So, but this was a game changer in the part that in FRB field, you have to be lucky. You look around the stars, you find an FRB, and then you just study it. But now we had a source which we know that where we have to look and when we have to look. So we did exactly that. We put in a proposal with GMRT, and we observed 4 bursts from the source in a 9-hour observation. These are the first reported FRB detection by any Indian telescope. Like, it's the first FRB detected by an Indian telescope. So this was all pretty exciting for me. And then it's also the widest bandwidth detection and lowest frequencies. And this FRB is also the only one yet, the first and only one yet that has been detected below 400 megahertz. It was first detected by Sardinia Radio Telescope, and then GBT and GMRT followed it. We announced our detection in Astronomer's Telegram. So GMRT is the most sensitive of the instruments at low frequencies. So we're actually doing a pretty in-depth burst property analysis, which is still going on. We are using data from
2 minutes left.
Okay, thanks. We have data from GBT as well as CHIME, which we have compound. And I told you earlier that about the downward drifting structure. This structure was called the SAT trombone structure. And since now we have the lowest frequency detection of the structure, and we have a very high frequency in time result from GMRT, we are trying to do an in-depth study of this structure and what exactly is happening and why we are seeing this structure. Is there a DM variation or whatever? So in future, we have also put in a proposal to monitor the source for 6 months, and we are also going to observe it in X-rays using AstroSat. So what can be the possibly happening is, like, there are many models which have come forward. There are three more prominent ones which I'm presenting here. Is that there might be a compact object which has been revolving around a very massive OB type star, and it is occulting the star, occulting the compact object, and whenever it comes in our line of sight, we see FRBs. There might be a precessing magnetar there, and which whenever it swoops across our line of sight, we see the FRBs. There's another possibility that there might be an extragalactic asteroid belt around a compact source which is blocking, and as it revolves around, it makes the source known. Well, we don't know anything for sure right now. There are lots of models, so lots and lots of observational evidence is required. Well, first we thought that this was the most exciting discovery of the year, but it was not. We have a galactic FRB now, and this FRB was detected after X-ray activity from a magnetar around 30,000 light years away. It was extremely, extremely powerful, as we expected from a galactic FRB. So this helped us answer that at least some FRB come from magnetars. And GMRT2 followed this up, but we didn't make any detections. We were able to put some good limits on what is actually out there. So we announced our findings in an anonymous telegram. So yes, FRBs are as exciting as they are unpredictable, and they have really changed a lot of things which we can do. Now we have an observational tools to study universe in ways which we were not able to earlier. FRBs are a very good probe to study the intergalactic medium, and they have helped tackle the missing baryon problem using the dispersion measure and redshift relationship, which was published by in Nature this year by J.P. McQuarrie. And if they are from neutron star, then really tell us that interesting things can happen with neutron star. They can also help us probe halos and study dark matter. And there are many questions still remain to be answered, that whether all FRBs repeat, whether all of them come from magnetars. And the interesting thing is that people have observed a tentative periodicity of 121102 as well. But so if it's true, then an all repeat is periodic or not. We haven't seen any other counterpart except the recent galactic FRB, so the X-ray. So this is all very exciting. It's a very new field. A lot of work has to be done, and it's a very exciting field for a new researcher like me. So thank you everyone for letting me share my work with you, and thank you Presision for giving me this unique opportunity to share my research at the undergrad. I'll take questions. Thank you.
Thank you so much, Ketan. It was a wonderful talk. Now we can move on to the question answer session. So if anyone has a question, then either write in the chat box or they can raise their hands.
There is already a question in the chat
Yes.
box.
Yeah. So I can see that Ritavan sir has raised his hand. So sir, please unmute yourself and go ahead with the question.
Yes, can you hear me?
Yes, yes, sir.
Yeah, so I was just wondering that when that one FRB was located in a star forming region in a galaxy, how was the location, how was it confirmed that it's not a foreground or a background source?
Well, first of all, this was located using the European VLBI network. So this is a network of telescopes all over Europe. So they form a very large baseline interferometer, and they're capable of detecting up to milli-arcsecond. Like they're very, very, very sensitive.
That's okay, that's okay, but that
Yeah, yeah,
constrains the angular position very well, but you don't know what's the distance. That's what I mean.
yeah,
So that's what I.
yeah. So distance was used using the dispersion measure. The dispersion measure of the source is around 349. So we modeled like what will be the dispersion measure in the direction of Milky Way, and then we also modeled around the intergalactic medium. So by the chance coincidence, like there was chance coincidence test which was involved in this study. Only this galaxy satisfied the entire dispersion measure budget, which is responsible for an FRB. So in the field of view of whatever the localization was, only this galaxy was capable of like the dispersion measure budget. Like if you include the Milky Way as well as the intergalactic medium as well as the host galaxy, only with modeling you can find that only this galaxy is responsible. So that's how we were able to localize it to this particular galaxy.
Okay, thank you.
Thank you, sir. The next question is from Abhinanda Chakraborty. So you can unmute yourself and go ahead with your question.
Hello, Ketan. Am I audible?
Yeah, yeah.
Yeah, nice talk. Can you please go to the slide where you showed the 4 FRVs you have detected? Yeah.
Correct.
So, yeah, that's one. So in this butterfly plot, I was just wondering, in the previous plot, there is no a signal in the lower part, but in the butterfly plot, you are getting a signal in the lower part. So how do you actually b- go from this plot to the butterfly plot?
Means
Can
in
you
which
just briefly? So in
which
the
plot to the
so in this third row, in the third row,
third plot?
this
Yeah,
is the butterfly
yeah,
third plot. Yeah, this
yeah,
is the
yeah,
butterfly
yeah,
plot, right? So can you
yeah.
just briefly tell me from second plot to third plot, how did you how have you done it?
Oh, okay. Well, the second plot is actually extracted from the fourth plot. So, in the fourth plot, we have actually is the main part. So, what Heimdall does is that Heimdall plots a dispersion measure with different, like it tests different dispersion measure at which the signal peaks, but it also has some sort of error in that. That's why you see this structure. So when you put in the filter bank file, uh, the particular pulse is it goes through a very rigorous process of step-by-step dispersion measured thing. So the at the and what dispersion measure, if the signal peaks at that particular dispersion measure, like they compare the SNR at at the dispersion measure at which you have the peak SNR is then plotted out. So the important thing is the fourth one. So in the fourth one, it's a frequency and time thing. So you have the sweep. So is this sweep is then like if you know the DM, you can actually shift the signals and arrange them in a straight line. So it is tested for different DMs, and whatever, and for the DM for which we get the maximum is then plotted out. So yeah, that's how it is done. It is done by trial and error. You get the DM by that.
Yeah. So no, my question is, how did you get the third one from a second plot or?
No, from fourth, not from second. Second plot is extracted from the fourth. Fourth is the main data.
Okay.
Thank you, Abhinanda, the question. So, do we have any other questions? Okay, so if not, then let's thank the speaker for the wonderful talk. And so we can move on to the next talk.
Okay. Thank you.
So the next talk is by Sriram Shankar, and he's going to talk about probing the circumgalactic medium using absorption line spectroscopy of background quasars. And he's from FISAT, Kerala. I would request Sriram to please share his screen and go ahead with his talk.
Thank you. Yeah. So good afternoon, everyone. So yeah, so I've been working in this for the past 2 years, which has resulted in a couple of papers, and I'm collaborating with Professor Anand at IIST and Professor Jane Charlton at Penn State University, Blair Savage at University of Wisconsin, and this is our work. We study the circumgalactic medium around galaxies. So firstly, I would like to start by telling you the questions that we ask. So these are the key questions that we ask. What is a CGM? Why does CGM matter? And how do we know what we know? This is what I'm going to briefly cover in this talk. So firstly, I'll start with a brief history. In 1950s, Guido Munch observed sodium-1 and singly ionized calcium, the spectra of hot stars at high galactic latitude, and followed by Lyman Spitzer, who later said that this must be pressure confined because of a hot extraplanar gas that is making this possible. And in 1963, quasars were discovered, which allowed quasar absorption spectroscopy. And we observe the spectra of background quasars, and we see a lot of absorption lines in the spectra. And later, Bakal and Spitzer, they found that they hypothesized that these absorptions originally arise from the CGM. Although it is not called that, this was the general consensus that was beginning to rise in that sense. So how would you define the CGM? So the circumgalactic medium is a multi-phase metal-enriched massive barium reservoir that resides in the extended dark matter halo of galaxies. So they share a symbiotic relationship with the host galaxy, where the host galaxy enriches the CGM and the CGM fuels star formation. So my work deals with studying these massive reservoirs using information conveyed by tiny ions through passerby messengers that were sent out across space-time by distant luminous sources. So some tracers that we use for this are Mg2, that is singly ionized magnesium. We have strong and weak classes, and then O6, which can have multiple origin scenarios. Then we have Lyman alpha lines, categorized broadly as DLAs, Lyman limit systems, partial Lyman limit systems, then the broad Lyman alpha, the neonate and magnesium 10, and we also get information from non-detections. So I would quickly explain what these things are. So just imagine Mg2, weak Mg2, C2, O2, weak lines like that. They trace like cold gas of the order of 10 raised to 4 Kelvin. And as you go higher up in ionization, you are tracing hotter and hotter gases, and you reach neonate and magnesium 10, which traces the warm ionized gas around 10 raised to 7 Kelvin. And the broad Lyman alpha also traces the warm gas. And then there are DLAs and Lyman systems, which are extremely dense hydrogen clouds, not molecular clouds. These are ionized hydrogen clouds traced by H1, the Lyman transitions. And these dense clouds have a correlation with galaxies, and they have a causal connection. So they are used to generally study the galactic, just outside the galactic disk and out to the circumgalactic medium, and even the IGM, which has weaker lines of Lyman series. So this plot, if you look at it, so what happens is if you have a Lyman line in 1 to 1.5 angstrom, that's the rest frame frequency, wavelength. As it gets redshifted, it goes higher up. So the formula goes as lambda into 1 plus z. So higher redshift you look, the higher the frequency, the wavelength is. So the plot on the top, the small plot, shows you the how the wavelength changes as a function of redshift, and you can see that the further back you look, the more information you get because of the wavelengths that we cover. Okay, so the high ions are X-ray detected. We can see that it's 08, 06, 07, not 06. And then there are UV detected lines like 06, neonate, magnesium 10. And there are intermediate ions traced by C4 and 06, 04. And then they have singly ionized lines like C2 and O2, probing much lower temperatures, and higher densities. So we extract the kinematics from the spectra by profile fitting. We superimpose the absorption feature with the void profile, which is nothing but a sum of Gaussian and Lorentzian. So that is Doppler broadening and pressure broadening. Pressure broadening usually happens due to collisions, which is prominent in hotter gases. And then we extract the component structure from high resolution spectroscopy, and then we analyze the system and identify multi-phase and try to find the origin scenario that makes such a profile possible. So if you look at this model, what you're looking at is a background QSO tracing a disk. So if you look at the left, you can see that it gets blue shifted and red shifted, and you can see a proper component structure. But if you look at the right, it's all kind of smeared together, and you get a really composite blended morphology. So if you look at the bottom, this is the composite spectra that we generally obtain with a lot of noise, and we identify these component structures and try to see what physical scenario makes this possible. So let's talk about gas regulation. So how does the CGM and the host galaxy interact? So host galaxy the two fuel star formation, they accrete gas from the CGM and also the IGM, and we can see accretion flows in spectroscopic signatures. And this is necessary to explain our models because the ISM gas depletion timescales are much shorter than what we find. What we actually observe. So there needs to be more supply of gas that fuels star formation, and that explains why there are still stars forming in the present day. And then we can see outflows, stellar feedback, and AGN feedback that enriches the CGM. So there is this word metallicity. So in the CGM, if we find high metallicity gas, it's generally a tracer of outflows because there is no star formation happening in the CGM. And there is galactic fountains, recycling variants happen in that. So old gases expelled from the galaxies cycle back to the galaxies, and they fuel star formation in the future. And then we have high velocity clouds and IVCs, intermediate velocity clouds, and they also have like transition temperature plasma in between them and the corona. So that is traced by O6, where the cold clouds like Mg2 hide in the center. And this helps us to study chemical enrichment history, and we can essentially say how these enrichment happens from pop-1 stars to pop-3 stars. So this is the work that we published in March of 2020, around March. And in this work, we studied a high velocity cloud in a galactic overdense region where there were multiple galaxies, dwarf galaxies, and 1.4 L star galaxy. So we essentially attributed what we find to the CGM of this 1.4 L star galaxies, with dwarf galaxies probably also interacting, but which is under the detection level of SDSS. So this is the structure we find. If you look at it, you can see that silicon 3 is kind of weak. C4 has a component structure. Hydrogen Lyman lines are broad. And with these information, we can, and if you look at O6, it's offset and it also has a component structure. So what that's telling you is it's probably a high velocity cloud with O6 tracing the transition temperature plasma, and which is probably also has a collision ionization origin. So that is what we find. And this is used as an Mg2 analog. So such studies are usually utilize Mg2 lines, but since the nature of our redshift and the wavelength band that we have available, we couldn't detect Mg2, but we found proxies for Mg2 in silicon 2 and carbon 2, which essentially trace the same gas because of the ionization levels. So this is a rough picture to keep in mind. If you look at the left plot, the DLA is in the center, and the lines like Mg2, they lie closer to the disk of the galaxy, and lines like C4 and O6, they lie much more further apart. Although this is a very, very crude model, we understand that it's a patchy medium in a sense, and there can be an incidence of different ions at different impact parameters, which is found by this recent paper on Project Amiga, which studied the Andromeda galaxy CGM, and they mapped where these different ions lie and how they are distributed. And that's a pretty neat work, and that shows how it has a patchy distribution and not a smooth distribution where you have clear distinctions of different ions tracing different impact parameters. If you look at the right, it shows a plot by Tomlin in 2011, which shows you that there's a fundamental distinction between quenched galaxies or passive galaxies and star-forming galaxies in terms of which can be detected in absorption lines in the CGM. So what it essentially says is that when you have detected detections of strong O6 in the CGM of a galaxy, it is likely that it's star-forming. That's what we obtained from this plot. And quenched galaxies regularly show weaker O6 at different impact parameters. So this is important because that shows you the direct connection between galaxy evolution and CGM, and how CGM plays a crucial role in this process. So this is Project Omega that I was talking about, where M31, the Andromeda Galaxy's CGM, extended up to, I think, 569 kiloparsec. And they
you have 2 minutes.
2 minutes, right?
Yeah.
Okay. Yeah. Okay. Yeah. So up to Arboreal, they find incidence of O6, and O6 goes even beyond Arboreal, but certain lines like Silicon 3 and Silicon 2, they are found much closer to the center of the galactic disk at low impact parameters. So this is my second work that currently recently got published. And in this work, we have a bright QSO at high redshift, and we study intervening absorption in that, and we try to attribute that to an environment. And we find that we are studying 5 systems in that, and most of the systems are indeed tracing the CGM from properties like O6 and Lyman partial Lyman limit systems and things like that. So we utilize we stitch data together. We utilize UV and optical, and we stitch different data together, and that's the wavelength that we obtain in the end. Total, we get 1,000 to 6,000 angstrom, which is a pretty broad window where we get a lot of diagnostic lines, and we can study multi-phase small-scale structure, which is really important. So this is one Lyman line we have, and we can see I've overplotted the contamination structure and the component structure that we find in that. It's a quite intricate process where you have to identify lines at different redshifts and eliminate the contaminants to avoid it polluting your data. So this is an extended system plot where you can see a component structure in C4, O3, O4. So we have information from all these lines, which is quite rare in most systems because of the wavelength range and the redshift range that we have available to us. We get information on all these lines, which gives us intricate information about the small scale physics of the environment, where we see gases coexisting in different temperature regime, which is essentially multi-phase. And that's a complicated process that simulations are still trying to model in the CGM. And we also have a problem with resolution that they're trying to overcome. So future work will be in that direction of trying to understand these multi-phase models. And with that, I think I'll stop. Yeah. Thank you.
Thank you, Sriram, for the wonderful talk. So I think now we are going to move over to some questions. So if anyone has a question, they can raise their hands. Okay, so I see that Alfred Mishi has his hand raised. So you can please unmute yourself and go ahead and ask a question.
Hello everyone.
Yeah, I can hear you.
Okay, thank you very much for letting me offer this one. I want to ask a very big question.
Okay, there's a voice break. It's not very clear.
Maybe he should write the question.
Yeah. You can write the question in the chat box, Alfred.
Can you hear me now?
No,
vaguely,
your voice
yeah.
is very cracked.
Very clear. You should write the question in the chat box.
I think by the time somebody else raised the hand, you can address that question.
Yes. Ritavan sir, you can please unmute yourself
Yes,
and go ahead with the question.
Can you hear me?
Yeah, I can hear you.
Yeah. So just to make sure, Alfred, your voice was not clear. So please write the question in the chat box while we discuss this question. So my question is, this is the relatively higher redshift, the one that you are talking about. Are you aware that so this Sanskriti Das and Smita Mathur et al. At Ohio State, they have recently sort of discovered X-ray absorption in from.
Sorry, the last part was not clear. From? Hello?
Sir, can you hear me? Okay, I think there is some kind of a connection problem with the one, sir.
Okay, so are we moving on to the next question or
let's hello, sir, can you hear me? Alfred has written his question, so we can move on to Alfred's question for the time being. What's the physical implication of your work? What physical problems can we use it to solve?
Okay, so a lot of things really. So the missing variance problem is most commonly touted as the impetus for this work, but recently it has been closed in low redshift. But FRBs generally give you an idea of highly ionized gas in the electron content from dispersion measures, but you still need to understand the implications of component structure and how these gases are distributed and in what phase they lie. And even in higher redshift, it's unlikely FRBs are going to help. So you still need follow-up observations in QSO spectroscopy to essentially understand how gas dynamics works at different redshifts. And this is important because our galaxy evolution models are still not entirely accurate, where we have hydrodynamic simulations that are implementing sub-resolution scale fixes to essentially replace observations. So what we do is we try to better constrain those models with observations, and we try to analyze this statistically and see, okay, what are the statistics of force absorption? So your models need to produce that much force at this impact parameters, and we essentially help constrain these models. And in the long run, we try to understand galaxy evolution more coherently. Does that answer the question?
Okay, I think, thank you, Sriram. So do we have any other questions? Okay. Okay, so I don't see any other questions in the chat box. I think Ritavan sir has been cut off for some reason. So if there are no other questions, I would like to ask a question.
Yeah.
Sriram, so actually what I understood by your talk is that when we look at a galaxy, there's kind of a stratification in the chemical composition. So towards the inner part of the galaxy, there's a particular elemental composition. As we go outward, there's a difference in the elemental composition. So is this composition somehow due to different stellar populations in the different locations?
So essentially, I'm talking about the circumgalactic medium. So that is the extended dark matter halo of galaxies. So there are no stars there. So once you are far from the disk of the galaxy, where all the stars are there are the galaxy extends to much higher lengths because of the dark matter halo, and as is evident from the rotation curves. So in these places, there are still gases lurking around that cannot be detected in optical or anything because they do not radiate light. So you need background sources to detect these things, and that is what I'm talking about. So this understanding of different elemental distributions at different impact parameters from the galactic center is just a crude way to kind of see that if you need, say, magnesium or some heavier elements, you need to have star formation nearby, which produces that element. So there is no real point thinking, okay, MG2 should be found in the virial radius, which is much farther from the galaxy. And you essentially kind of intuitively understand that if you have heavier elements, they're likely that they are close to the center of the galaxy. Just like how Lyman alpha lines, the damp Lyman alpha systems, which are very optically thick hydrogen absorbers, which are found close to the galactic disk.
Okay. Thank you, Sriram. So do we have any other questions? I don't see any other hands raised or anything in the chat box. So if not, then we may conclude this session. I would like to thank all the speakers for their wonderful talks. truly we had a very good astrophysics and cosmology session today. Now I would like to hand it over to Moitreyo for further announcements.
Yeah, thanks to all the speakers. Those were some very illuminating talks, and thanks also to everyone for attending. So we have two more events today. From 2 p.m., we have the interdisciplinary session of the symposium, where we will also hear some of such exciting talks. And we also have a panel discussion session from 4 p.m. today, where some eminent scientists will be joining us for a very interesting discussion. So yeah, we hope to see you all there. Thank you.